All right, in this homework, we've got some more theorem stuff and optimization. I'm going to focus mostly on the optimization, but I'll do a couple theorems ones. Let's start with number 2. Number 2 is if p of x is a continuous function in the closed interval with p of 1 less than or equal to k is less than or equal to p of 3, and c is in the closed interval from 1 to 3, which of the following statements is true? So this type of problem, you really want to be able to characterize each thing as true or false. And I like to think of it in two ways. The first way is you can kind of get a picture in your head of what's actually happening here. So p of 1, who knows what it is, but we're going to call this p of 1. There's also p of 3. Who knows what is going on there, but there's some sort of p of 3. And it could be that p of 1 is higher than p of 3. We don't know. And there's a k somewhere in between there. So somewhere there is a k that is between p of 1 and p of 3. Okay. C is somewhere between 1 and 3. Okay, that's all we know. So option A says, oh, the other thing is after we draw a picture, we can think what theorems apply. So let's look at the things we have. We have a continuous function on a closed interval. But notice it is not differentiable. So the intermediate value theorem, which says that all the y values in between the starting point and the ending point have to happen somewhere, that has to be true, and that looks like what this one might be about. That applies. Also, the extreme value theorem from the first semester that says that somewhere in between here, there has to be a local minimum, an absolute minimum and an absolute maximum, either at the endpoints or at the critical values. Probably not going to be about that, but it might be. What doesn't apply is the mean value theorem and Rolle's theorem. Those don't apply because we don't have a differentiable function. This first one says p of c, so the y value at c has to be equal to p of 3 plus p of 1 divided by 2. That's the average. It's saying like, hey, the y value at c has to be exactly halfway between here, and there's no reason that's true. Like you could have something like that. I don't know. Okay. And also it'd have to be true for all different c's because we don't know exactly where c is. The second one is p of c is p of 3 minus p of 1 divided by 2. And that's actually the slope. That would be the slope. Why does p of c have to be the slope? Well, the mean value theorem doesn't apply, and we don't even know like which c we're talking about. So that's no good. There's at least one value c such that p of c equals k. So it's saying there's some place in between here where the y value has to be k. And that is guaranteed to be true somewhere because of the intermediate value theorem. And whether it's here or here, for some value of c, p of c has to be k because that's what the intermediate value theorem says, and so that's going to be the true one. Let's look at the other ones, though. So let's make sure we know this all the way. When we're doing our homeworks, by the way, we don't want to just stop with, like, find the right answer and be done. Let's make sure we understand what is going on. There's only one value c such that p of c equals k. Well, why does there only have to be one value of c where that's the y value? Maybe it looks like this, where there's a few different values of c where the y value is k. So that doesn't need to be true. And the last one says c equals 2. Why? I don't know why that would need to be true. So this is the only one that has to be true. Okay, let's do another one. This is a calculator mean value theorem one. And it's a little bit different setup, so we'll take a look at it. We've got this function. It's a cubic. I'm going to draw it real quick because I know what cubics look like. Okay, so there's this cubic, and it's in the closed interval between a and 2. The value guaranteed by the mean value theorem is at c equals 1.72. So 1.72 is the one that's in between a and 2. And at that value, there has to be, the average slope has to be equal to the slope right then. So the first thing I'm going to do is I'm going to find the derivative. 3x squared, and so f prime of c is f prime of 1.72, says that's the c. And this is why we need a calculator here. Nobody wants to do this without a calculator. This is 3 times 1.72 squared, which is 8.8752. So that's 8.8752. And what the mean value theorem says is that this is the slope at 1.72. that has to be equal to the average slope. Well, how do we find the average slope on this interval? We need the starting point and the end point. The starting point is a, comma, a cubed plus 2. Okay, that's our point. When we plug in a, we get a cubed plus 2. Okay. Our second point is 2. That's the x value. And when x is 2, y is 10. So y2 minus y1 over x2 minus x1. And this looks like a pretty tough equation to solve, except you have to remember you have a calculator. And when you have a calculator, you can just solve by graphing. You graph y equals 8.8752, and y equals 10 minus a cubed. In this case, we have to put in x, so x cubed plus 2 over 2 minus x, and we're going to graph it. And I noticed there are two intersection points. Either one of those could be answers. The first intersection point is 1.424, which is this answer. And you'll notice that all the answers are positive, so it's not going to be this other intersection point, even though it would have been a correct solution. So this is our answer by solving this in a calculator. You do want to know that skill of like, hey, when you run into a tough equation to solve, looks tough, but you've got a calculator, just graph it. All right. I think I will move on to optimization problems. Okay. There are 50 apple trees in an orchard. Okay. Each tree produces 800 apples. So each one of those 50 trees produces 800 apples. So right now we're making 40,000 apples. That's a lot of apples. For each additional tree planted in the orchard, okay, so we could have more than 50 trees, the output per tree drops by 10 apples. So I can make more trees, but if I do that, the trees will produce fewer apples. Okay, so if I make like 800 more trees, they'll all be producing 0 apples, maybe because they're too crowded together. I don't know. How many trees should be added to maximize the total output of trees? Output of the trees. This is a pretty classic economics problem, this type of thing. So what we need is an equation for the total output, and then we're going to maximize it. So the total output, or the number of apples, will be equal to the number of trees times the number of apples per tree. And the number of trees is equal to the 50 we started with, plus the actual question is, how many more trees should be added? And that's going to be, I'm going to call that x. I guess I could have called it t for trees. 50 plus x will be the number of trees I have, the 50 I started with, plus however many I added, times the number of apples per tree. Well, there's 800 apples per tree, but every time I add a tree, so however big x is, we decrease this by 10. So there'll be the 800 apples minus 10 times however many trees we added. So this number and this number are the same, right? We add more trees, but we produce less apples, fewer apples per tree. So the number of apples we'll produce will be 40,000. I'm going to multiply this out. I could use the product rule, but I don't feel like it. Minus 500x plus 800x minus 10x squared. So a is, I'm going to rewrite this as negative 10x squared, combine like terms. And what we're doing when we're maximizing is we're using the extreme value theorem, which says that, hey, either when we have 0 added, when we have no extra trees added, that might be the maximum, or maybe it's going to be like somewhere else. Well, I know for a fact this is a parabola, and so wherever the critical value is, that's going to be the maximum value. So I don't need to do the candidates test. I can just straight up find the derivative, find where the slope is 0. That will be where the maximum occurs. So I'm going to find the derivative. I'm finding the slope of this. This is negative 20x plus 300. And we want to set it equal to 0. Where is the slope equal to 0? This is the critical value. And we subtract 300 and divide by negative 20. X is 15. Let's make sure we've actually answered the question here. How many trees should be added? We should add 15 trees. That's the answer because that will be where the slope is 0. That's the top of the problem. Great. What other optimization ones do we have? Okay. Construct a window in the shape of a semicircle over a rectangle. So, okay. I guess there's not like this, right? But there's a semicircle above a rectangle. Here's our window. That's kind of pretty. If the distance around the outside of the window, remember this whole thing is our window, is 12 feet, what dimensions, so the perimeter has to be 12, what dimensions will result in the rectangle having the largest possible area? So this is the actual thing we're trying to do. We're trying to maximize the area of this rectangle. So I guess I'm going to need a variable. This is x, call this y, then this will also be y because it's a rectangle. I'm trying to maximize the area of the rectangle, which is x times y, length times width. Now if I have two variables, I can't take the derivative yet, or at least you guys don't know how to yet. So I need to get it down to one variable, and I'm going to have to use this additional piece of information that the perimeter is 12. So the perimeter is all the way around the outside. And the perimeter is x plus 2y's plus, I need to find this. Now this is a semicircle. So a semicircle, I guess I should find the area of the whole circle first because we have a formula for that. The circumference of a circle is 2 pi r. And the radius of this particular circle, I don't need a new variable because I know the radius has to be half of whatever x is. So the radius equals 1/2 x. So the circumference of this circle will be 2 times pi times 1/2 x. 2 times 1/2 is 1. Pi times x is just pi x. But that's the circumference of the whole circle. So the circumference of the semicircle is 1/2 pi x. Okay. So that's the other part of this perimeter. X plus 2y's plus 1/2 pi x. So far we've just done a geometry problem. And this equals 12. Now, I'm going to need to substitute one of these variables. It looks to me like it is much easier to solve for y than x. So I'm going to do that. I'm going to move the x's to the other side. 12 minus x minus 1/2 pi x. And divide by 2. 12. I'm going to go ahead and just divide everything by 2. 6 minus 1/2 x minus 1/4 pi x. So that's y. I'm going to plug it in. So the area equals x times all of this. So 6x, because I multiplied x times 6, minus 1/2 x squared. Again, I'm multiplying x times y. Minus 1/4 pi x squared. And just like always, I am trying to maximize this. So I'm going to take the derivative and see when the change is 0. When it stops getting bigger and starts getting smaller. 6 minus x minus 1/2 pi x. I want this equal to 0. So I'll subtract 6. And this is just a tricky looking linear equation, but it's still a linear equation. I'm going to factor out the x. -1 minus 1/2 pi. And divide by the thing that's multiplying by x. So x is -6 divided by -1 minus 1/2 pi. To simplify, we don't want to really leave negatives in the denominator. We also don't want fractions in the denominator. So I'm going to multiply by -2 over -2. If you didn't simplify, it's not the worst thing in the world, but 2 plus pi. That is what x needs to be. As for the dimensions, so I guess I should go ahead and say that if this is x, y will need to be 6 minus half of this will be 6 over 2 plus pi, minus 1/4 of this will be minus 3, and then times pi, 3 pi over 2 plus pi. Yuck. So I guess those are the dimensions. This could probably be simplified. Ooh, in fact, maybe I should simplify it. Let's put this 6, to put it over a common denominator, I'm going to put it over 1 and then multiply by 2 plus pi over 2 plus pi. So 6 times 2 plus pi is 12 plus 6 pi over 2 plus pi. And when I subtract these now, 12 minus 6 is 6. 6 pi minus 3 pi is 3 pi over 2 plus pi. And that looks a little bit better. So y equals 6 plus 3 pi over 2 plus pi. All right, I'll do one more optimization. I'll do all the optimization problems here. This will be my last one. I'll try to go quickly. An open rectangular box. So here is my attempt at a box. And here's the top, and it says it's open. The top is open. With a square base. So, man, oh man, I lost track of where the top of my box is. Oh my gosh, I hate it when this happens. When you, like, can't tell where the top of the thing you drew is. Oh my gosh, I have to redraw my box. This is so embarrassing. I can't find my top. I lost it. Oh, now I see it. Okay, no, this is the top. Cool. Okay. So this is the base right here, and this is a square. So I'm going to call this L and this L and this L and this L. These are all L. And this is going to be the height. Okay, all these things sticking up are the height. We want the largest possible volume. The volume is L squared times H. And we want to maximize this, but again, we have to get it down to one dimension. And so we're going to use this surface area information, which is the L squared. That's the base, L squared, plus each of these sides is going to be L times H. It's going to be 4 of those, 4LH. That has to equal 48. The easiest variable to solve for here is H, it looks like, because there's only one H. So I'm going to subtract L squared and divide it by 4L. All right, so this is what I'm plugging in for H. So V equals L squared times 48 minus L squared over 4H, or 4L, sorry. And I can cancel out one of the L's that's dividing with one of the L's that is multiplying to get, I'll multiply it across the top two. I'll also do, well, okay, so 48L minus L cubed over 4, which is, I'll divide everything by 4. 12L minus 1/4 L cubed. This is what we're maximizing. It's an easy derivative to do. We're going to take the derivative, 12 minus 3/4 L squared equals 0, and now we're just solving. Negative 3/4 L squared equals negative 12, multiplied by negative 3/4. L squared equals 16, so L is going to be 4. The length can't be negative, so we're not going to do the plus or minus square root. If the length is 4, I can plug in right here and get that the height has to be 2. 32 divided by 16 is 2. And so those are the dimensions that maximize the box's volume. All right, hopefully that's helpful.